I'm going to make an announcement about this. So I received several emails begging me to let you have a little bit more time with that new question that I changed with number 4. And I really want you to think about that question because that's an important question. So I'm willing to make a deal, but there has to be something on your end too. By the way, so maybe you saw in the new homework that it says in San Francisco it's due on Wednesday and in Colombia it's due on Friday. This is not because I'm being more generous to them. The thing is that they watch the lectures 2 days later. So don't think that they're getting a special deal that you're not getting. But what I wanted to offer to you was that I will let you turn in this homework, but I don't want you to get used to it. But I'll let you turn the homework in on Friday, but every single person has to write at least half a page for that bonus question with some serious ideas. Okay? Doesn't mean you have to solve it because it's a difficult question, but you have to show to me that you thought about it seriously and you have some ideas. Or you can turn it in today. That's fine. So the original part A was false, the way that I had it originally written. That's right. And I think Laura put a counterexample on the forum, which is what made me realize that it's a small problem with that. But so it's up to you. You can either turn it in now or turn it in on Friday, but then you must give me some good ideas about that bonus problem.
Right now you mean today. Yeah, can we email it to you by midnight?
Oh yeah, so that's the other thing. So you can either turn it on paper today or on email by midnight. And by the way, so please remember to do this. I'm trying to keep the homework in a separate account because my inbox is a mess and I want to make sure I don't lose anything. So homework goes to a special email that I made, which is this one. This was taken, can you believe it? cca.acc. It was taken, so I had to do this.
Whoa.
I don't know. I didn't get any more creative than this. So if you are going to turn it in by email, then that's where you need to send it. The other thing that I wanted to announce is that there's a couple of people that can't make my office hours as it is right now, and I think that everybody will be able to make it if I make a very small change. They're going to be Mondays from 1:30 to 3:30. So they were 2 to 4, so if you could make 2 to 4, that means you can probably make some of this stuff. But I want to allow people to arrive before 2. Okay? So these are the 2 announcements. Okay. So let's go back to proving some theorems. We were talking about reduced Groebner bases, right? So I said a Groebner basis is reduced if all the initial terms, I guess I called it G1 up to GM. So each initial term is supposed to be monic. And the other thing is that no monomial term in GI is a multiple of some other initial term. So that's what makes a Groebner basis reduced. And we were in the middle of proving this theorem. It's a very nice theorem that says that given an ideal I and a monomial ordering that I call less than, there is a unique reduced Groebner basis. Okay. So that's the theorem that we're proving right now. And I said that the way, well, to prove this we need to prove two things, existence and uniqueness, right? So to prove existence, I basically showed you how to do it last time, but let's go through it again quickly. So I actually tell you how to do it. So the first thing is you just make each initial term monic, and that's easy because you just divide by the first coefficient. Then I said that you would delete unnecessary GJs. And what I mean by this is that I delete the GJs in this situation. If the initial term of GJ is multiple of the initial term of GI, then I don't need this guy to generate anything new because this guy is already generated by this guy. So I delete those. Okay? And by doing that, I have a minimal Groebner basis, but this is a stronger condition than minimal. And so to make it reduced, what I do is that I divide each GI by the other guys. Using long division, and call the remainder Ri. Okay. And remember that the result of this division might depend on choices that we made here because we don't know that these guys are a Groebner basis. We know that all of them are a Groebner basis, but once I delete GI, that's not going to be a Groebner basis. The answer might depend on choices, but so we just say, okay, we'll divide GI in any way and get some remainder and call that remainder Ri. Okay? So I'm claiming that those Ri's are going to be a Groebner basis, but reduced. So my claim is that R1 up to Rm is the reduced Groebner basis. Okay. How can I say this? Well, the reason is this. Let's look at this step, which is the key step. You divided each GI by the other ones. And so the answer that you got looks like this. The term GI is missing, right? This is not there. You got this, right? And now, remember that when you do this, there's two things that happen. The first condition is that the initial term of GI is greater than or equal to the initial term of A, J, GJ for each one of these guys. And the second thing that occurs is that no monomial in R is divisible by one of these initial terms. Okay. Those are the two conditions for long division. That's what we can accomplish. And this is the guy that I'm calling Ri. Right? So the first thing I'd like to point out, I said this last time, is that if you look at the initial term here, right, there's something here somewhere you see the initial term of GI. Okay? And you see that initial term cannot appear in any of these guys. Because the initial term of GI is not a multiple of the initial term of one of these other guys. Okay? So that means that the initial term of GI is not in any of these terms, so it survives all of these terms and it has to be here. Which is why I said that the initial term of GI is equal to the initial term of Ri. And so that means that because the initial terms of all the GIs generate, that means that the initial terms of the RIs generate because they're the same guys. Okay? But now if you look at this other condition, this condition says that no monomial in Ri is divisible by an initial term of Gj, but the initial term of Gj is the initial term of Rj. And that means that the condition that I wrote here is exactly the defining condition of a reduced Groebner basis. And that's what makes this argument work. Do you guys have any questions about that argument?
Yeah, I got one question. I got one. I don't see why the initial term of GI has to be the initial term of RI, not just the whatever function.
Because if Ri had any bigger terms, then GI would have them also. If Ri had any larger terms, any terms larger than this initial term of GI, then that term would have to be here also. And that means that this guy would not be the initial term. The thing to remember is that this initial term of GI is the biggest term in this whole equation. Okay? So it appears here, and if it doesn't appear here, then it has to appear here, and it has to be the biggest guy there. That's fine. Yeah? Yep.
Notationally, you have G sub I is equal to A sub I, G sub I. Is that different I than I?
So this is that notation that I said last time, that when I put a little hat over it, I mean that this expression is not really, this term is not here.
Oh, okay.
So all the other A, J's, G, J's are there except for this one. Which is why that equation makes sense. Okay. So that's existence. Now, what about uniqueness? So uniqueness is fairly easy also. Let's just suppose that you have two different reduced Groebner bases. So are reduced Groebner bases. Okay? Now remember that reduced implies minimal, right? Because the definition of minimal is almost the same one, but with a weaker condition here. So I told you that you're going to prove something in your homework too. You're going to prove that any two minimal bases share two properties. The first property is that they have the same number of terms. Right? So here, I stated this explicitly last time. And this is something that you're going to show in homework too. The first thing is that M is equal to R. Okay? Any two minimal Groebner bases have the same number of elements. But the second thing is that not only do they have the same number of elements, but actually the initial terms of these guys are exactly the same as the initial terms of these guys. Okay? And so I can assume that the initial term of G1 is equal to the initial term of G prime 1, etc. And then I say the following. I'm going to say, I don't know, let's say, my goal is to prove that these guys really are the same reduced Groebner basis, right? And so let's just suppose that they're not. So if G and G prime are not different, then at least one of the terms is different. So let's say that Gi is not equal to G prime I, okay? And so let's call Fi their difference. And then I say this. I say that Gi and G prime I are elements of I, right? Because they're elements of a Groebner basis of I. And so that means that the initial term of Fi is in the initial ideal of I, right? But then I say this. I say, well, the initial ideal of I, G is supposed to be a Groebner basis, right? And so that means that the initial ideal is generated by initial term of G1 up to the initial term of Gm. Okay. And again, because of this homework problem that you just did for the homework due today, if you have a monomial, because this guy's a monomial, and it's a member of this monomial ideal. When I say monomial ideal, I mean an ideal that's generated by monomials. The only way that can happen is if this guy is a multiple of one of these individual generators, right? So let's say that is Gj for some j. Okay. Well, the first thing I will say is that, I mean, there's two cases. Either j is equal to I or j is different from I. So let's consider those two cases. J equals I, and bj is not equal to I. The first case is easy to eliminate because the initial term of Fi, because Gi and Gi prime have the same initial term, that means that when you take Gi minus G prime, you cancel that initial term. Okay? So that means that the initial term of Gi minus Gi prime is not the initial term of Gi, it's something smaller. Okay? So this is the initial term of Fi. The initial term of Fi is smaller than the initial term of Gi, and so there's no way that the initial term of Gi divides the initial term of Fi because this one's bigger. So this is a contradiction. So this can't be. Okay? So that it must be that we're in case we're in this case. Okay? The initial term of some other Gj divides the initial term of Fi, which I'm going to rewrite as Gi minus Gi prime. Okay? But the thing is that the initial term of Gi minus Gi prime is either a term of Gi or a term of Gi prime. So this is either a term of Gi or a term of Gi prime. Right? There's no other choices. And I'm saying that the initial term of Gj divides it. But you see, G is supposed to be a reduced Groebner basis, and so it can't be that the initial term of Gj divides a term of Gi. So this can't be. But now you have to remember that the initial term of Gj is also the initial term of G prime J. Okay? And G prime is also supposed to be a reduced Groebner basis. And so it can't be that the initial term of G prime J divides some term of Gi prime. This can't be either. And so in either case, I get a contradiction. And that finishes my proof. So that proves uniqueness, and that proves my theorem. This is a good time to ask me any questions about this. Yep.
In the first part, because G for the first X total.
Here.
Was that because GI was or GJ?
The contradiction that I had here is that if I had that the initial term of Gj divides a term of Gi, then that's going to be a contradiction to the definition of reduced basis, Groebner basis. Because I said that G is supposed to be a reduced Groebner basis, and the definition of that is precisely that this is not supposed to happen, that no term of Gi is supposed to be a multiple of the initial term of some other Gj. And then the other contradiction is the same, but instead of G, we use G prime. Any other questions about reduced Groebner bases? Okay. Well, let me show you then another application of Groebner bases, which is very nice. So another application of Groebner bases. It's the following question. Let's say that I give you two ideals. How can you tell if those ideals are the same ideal or not? And let me give you just a concrete example. I give you some ideal. It might look like this. So that's some ideal of polynomials in two variables. I give you a different ideal that maybe looks like this. And I ask you, are these guys different or are they the same? And I mean, they look different, right? So, I mean, as far as we can tell, they don't even have anything in common. So how do you answer that question? I mean, if you hadn't taken this class, if you were not enrolled in this class, and someone asked you this question, how would you go about it? Any ideas? I'm sorry?
See if every element in I is an element in J.
So you would try to see if basically both inclusions. You would try to see if every element that's here is also here, and then see if every element that's here is also here. So how do you check if every element of I is in J? Well, the good thing about that is that you just have to check generators. If this guy is in J and this guy is in J, then the whole ideal is going to be in J. And so you could really just proceed by saying, well, let me just see if I can write this guy as a combination of these three. And see if I can write this guy as a combination of these three. And if that works, that means that I is a subset of J. And then I could do it in the opposite direction and decide whether J is a subset of I. And then I would be able to answer this question. So this is in theory, but I don't know. Imagine that you have two ideals that are huge and they have 50 variables and they have 100 generators. Okay? And so you would have to say, okay, well, I have a polynomial in 50 variables, and I have 100 polynomials here, and I have to decide if this polynomial in 50 variables is a combination of these 100 polynomials. Okay? So how do you decide that? Well, that's not so easy anymore. Right? And we actually do want to be able to do computations like this. I mean, sometimes ideals in nature are big, and you have to deal with them. So I think that this is this method that we just mentioned is something that might work for small ideals, but for big ideals, it's kind of not very practical. So what do you do then? Well, here's a theorem. And when you think about it, actually, there isn't a lot of content to this theorem. What I'm going to do is just pick a random order of the monomials and find the reduced Groebner basis for this guy and find the reduced Groebner basis for this guy. And I claim that the two ideals are equal if and only if the two reduced Groebner bases are equal. So how do I do this? I said I pick any monomial ordering and then I compute reduced Groebner bases. Let's call it, let's say that G is the Groebner basis of I and H is the Groebner basis of J. Okay? So my claim is that the two ideals that I started with are equal if and only if the reduced Groebner bases with respect to this random order are equal. Okay, how do I know this? The proof is really very simple. You see, if I is equal to J, then they're the same ideal, and I just proved that every ideal has a unique reduced Groebner basis. And if G and H are reduced Groebner basis for it, then they must be the same guy. So this is just clear from the uniqueness of reduced Groebner basis. If they're the same ideal, then they must give me the same reduced Groebner basis. And for the other direction, it's, I don't know, maybe easier. If G is equal to H, well, I is the ideal generated by G, and J is the ideal generated by H. So if G is equal to H, then they generate the same thing. And this happens to be called I, and this happens to be called J. So that is probably one of the easiest proofs we're going to see in this class, but it's a very powerful one, you see, because you can actually do this. And I did actually show you algorithms that are reasonably practical for computing, first of all, for computing a Groebner basis, and then for reducing it. And that means that you actually can carry this out. And not only can you carry this out, but actually you can do this with respect to any monomial ordering, which can be an advantage because you can kind of spot your ideals and maybe you can sense that a certain monomial ordering is going to be very helpful. So you just pick that one. You have that freedom to do it with whatever monomial you prefer. So you do this in this example, and you find that you do get the same Groebner basis, the same reduced Groebner basis, and that's. I mean, I'm going to write it out, but of course you have to do it, right? It's work. I'm not saying that you get this for free, but now we know how to do it, and when you do it, you get this. You guys have the same reduced Groebner basis, so the ideals are equal. It's a very nice application. It's another nice application. Something called elimination theory. The elimination theory is a method for, if I give you a bunch of algebraic equations and I ask you to solve the system of equations. So this is about solving systems of polynomial equations. So I don't know. What kinds of systems of equations do you guys know how to solve?
Linear.
Linear, right? If I give you a system of linear equations, I could ask you to do it in many variables, and you can do it, right? In 100 variables, maybe. I mean, well. Yeah, I prefer not to either. But let's say you like for 5 variables, you prefer not to, but you could do it by hand. How do you do it? Kind of solve for x5, then you solve for x4, then x3, etc. And you can do that either by hand or using the usual Gauss-Jordan method, or any of these things. What other kinds of polynomial equations do you know how to solve? Yeah, me neither. I mean,
Single variable quadratic equation.
single variable quadratic equation. That's good. I mean, so you know how to do that, right? So I give you 3x squared plus 7x plus 9 equals 0. You can do it. How about single variable cubic equation?
Ugh.
One equation in one variable, degree 3. X cubed plus x squared minus x plus 1 equals 0. Do you guys know, so the story is that it is possible, and there is a cubic formula that does this for you. It's called Cardano formula. And for a single variable at degree 4, there is some other formula, and it's horrible, it's huge. You actually never see it written explicitly. It's just that horrible. But it exists, but you probably are aware of the fact that that's the end of our capabilities as human beings. Actually, it's not just as human beings, because the point is that if I give you a random equation of degree 5, then there's no formula that I can solve. That's one equation and one unknown and degree 5. Okay? So when I tell you that I'm going to teach you to solve systems of polynomial equations, you should be very skeptical, because you know that I cannot teach you how to solve one equation in one variable in degree 5. But let's see what we can do. I mean, we still want to be able to do something. Right? So let me show you a harder system of equations. So there's one equation, and there's another equation. guys know about the system of equations?
It's like at most 4 each.
At most 4 solutions. Why is that?
It's like the possible intersections of an ellipse and a circle.
So somehow in your head you figured out that this is an ellipse. And it is an ellipse. You can do it. And this is a circle. And an ellipse and a circle can intersect in at most 4 points. So that's what we know, and that's kind of the extent of what we know. We can do a little bit better, and if I actually give you enough time, you can play with these equations and solve this. Okay. How would you do it? Well, maybe you would try to do what you do in the linear case. If you have 2 linear equations and 2 unknowns, you solve for one variable and then for the other. And so what you can do is kind of take the system of equations and then try to find some clever manipulation until you can figure out what y is, for example. And it's possible. So if you do some clever algebra, you're going to find that 5y to the 4th minus 4y cubed is equal to 0. And that you get by just combining these 2 equations. And play with it long enough, you get this. Okay. And so that means that y is equal to 0 or y is equal to 4. And once you get to this point, then you can do it, because basically for each one of these guys, you can plug back in, and you're going to get 2 quadratic equations for x, which, well, you can solve both equations and hope that you get the same answer for both equations. It turns out that sometimes you do and sometimes you don't. But once you go from here, it's easy to see that with y equals 0, x is equal to 1 is okay, but x is equal to negative 1 is not okay. And from this equation, you see that x has to be 1 or negative 1. But from this equation, you get that x should be 1 or something different. So you get that x is equal to 1. And if y equals 4/5, then you do the same thing. From this one, you know that x is either 3/5 or negative 3/5. And it turns out that only one of those works. And so the solutions are 1, 0 and minus 3/5, 4. That's it. Now, what we might try to do in general is basically the same thing. And that's what elimination theory is about. So, system of equations. F1 of x equals 0 up to Fn of x is equal to 2. If you think about it, this is the same thing as saying that f of x is equal to 0 for all polynomials in the ideal generated by f1. It's called an ideal I. Why is this? Well, this direction is trivial. If f of x is equal to 0 for everything in this ideal, then in particular, f of x is equal to 0 for f1 up to fn. So the direction is trivial. This direction is also pretty easy, because if x is a root of f1 up to fn, there's going to be a root of any combination of them. So it's going to be a root of that. So in other words, a system of polynomial equations is more or less the same thing as an ideal in a polynomial. And so we want to solve, we want to find this. The goal, compute the set of the space of polynomials, sorry, the space of solutions be the same thing? Well, I have actually, so I have n variables, okay? And so what I'm going to try to do is basically see if I can find out what the last variable is. Okay, so idea, which is what I did here, I found an equation involving only y, and that's how I managed to find y. And so the idea is see if I can find a polynomial equation to look for an equation p of x equals 0, an equation in the ideal, of course. And solve it. Like I said, I want you to be skeptical about my method, and this is already a place where there's very big limitation. Because I'm assuming that I know how to solve this equation, and maybe I don't. I only know how to solve very simple equations. But okay, so elimination theory doesn't always work, but it works sometimes, and that's better than nothing. Sorry, I meant an equation that only involves the last variable. If I manage to do that, then I want to find the previous variable, like xn minus 1. So my next step would be to look for an equation that looks like maybe some polynomial that maybe only involves xn minus 1, or maybe it involves xn minus 1 and xn, because I already know what xn is. And then solve it for each solution of the first equation. And then that means that I know what the possible values of xn and xn minus 1 are, and I continue doing it. I look for an equation involving only xn minus 2, xn minus 1, and xn, etc. So this is the technique of elimination here. And the point is, can we do it? I want to define some ideals which are basically going to be the ideals of polynomials involving only some of the variables. So the elimination ideal of I is denoted I sub I, and it consists of the polynomials in I which only involve the last variables. They only involve the variables x I plus 1 up to xn. For example, what I'm looking for here is a polynomial in the n minus first elimination ideal. It only involves the variable xn. What I'm looking for here is a polynomial in the n minus second elimination ideal. I only wanted to contain these variables. So the point is that this technique of elimination works if we have a decent way of computing these elimination ideals. So elimination theory will work only if we can compute these guys. In other words, bases are amazing, and they can tell you how to do this. So here's a nice theorem. It says that, let's say you have some Groebner basis for your ideal. A Groebner basis for the ideal with respect to the lexicographic order where x1 is the biggest, x2 is the next one. And we already discussed that we can compute this explicitly fairly easy. Now, what I'm going to do is that I'm going to look at these polynomials. Remember that my goal is to look for polynomials in my ideal I that only involve certain variables. And a natural place to start looking is here. I have some polynomials in I. Let me see if these only have those variables. And if they do, let me put them in something called GI. So there are the polynomials in G involving only the last variables. Symbols, this is just G intersected with the polynomials in the last variables. Now, if you know G, then computing GI is immediate, right? You just look at the polynomials, and for each one of the polynomials, you just see, do they have the variables, or do they have extra variables that I don't want? Well, it's amazing. So this ideal I sub I is generated by these guys, and not only that, these guys are a Groebner basis for that ideal. So GI is a Groebner basis for my ideal I sub I with respect to the order the lexicographic order, and now we're talking about polynomials that don't involve the first I variables, so those variables are not going to enter my order, only the last one. Okay. So this tells you that basically doing this computation in practice is amazingly easy. You just find a Groebner basis, and then, for example here, how would we have done it? You just find a Groebner basis for the ideal given by these two equations, and then this theorem tells you that this polynomial that you see here must have been generated by one of the Groebner basis polynomials. In other words, this polynomial was basically part of your Groebner basis. And that this lets you do this very explicitly. The proof of this is not too difficult either, but I think it's going to take me longer than 2 minutes. So maybe I'll stop there and just take questions. You guys have any? Maybe one thing that I'll do is actually give you an explicit system of polynomial equations and make you do this, so you see that how easy it is. It's very explicit. Okay. So in case you arrived late, I said that you can either turn in homework 1 as it is right now, or you can turn it on Friday, but your homework must contain interesting, good ideas about the bonus problem. So it's your choice what to do.
Nobody isn't